I grew up in Canton, Oklahoma, on a farm, a dairy farm, and left there and came to the University of Oklahoma. I had some exposure to science in the high school. I blew up the chemistry lab, so I decided I shouldn't do chemistry when I got here. So I went into math, and I got my BS in math. And then I was very fortunate that Professor Jenny Rude Nielsen recruited me to get a PhD. I joined a very fine fraternity here called Delta Tau Delta. And those made my close friends for life, and a few of whom are here in this audience, and I'm very pleased with that. After I graduated, I was in ROTC, Air Force. So I got to choose, and I went to the best lab that the Air Force had. It was in Boston, Massachusetts, called the Air Force Cambridge Research Labs. And the first thing they said is, my job was to create some instruments to measure something, and they couldn't tell me what it was because I didn't have a clearance. So I had to design to measure this unknown source, didn't know how bright it would be. Instruments were going to be on the ground, on balloons, on airplanes. And so they went on for a year, and I did that. I designed a set of instruments to do that. And finally I got my clearance, and it turned out immediately we started putting those instruments on airplanes and the ground to measure the first United States high-altitude nuclear bursts that were going on in the Pacific. We found some extremely interesting things in the measurements. So I set up a laboratory and a field program to learn the fundamentals of that problem. So a large part of my career had to do with measuring the upper atmosphere, and we measured the aurora. We did that with an airplane, significant, but still you have to look through some of the atmosphere. So then we put a program together with about 25 rockets over a period of 12 years or so. That program was called IceCap. And we measured the first infrared energy from the aurora. And we finally understood the fundamentals of what goes on in the upper atmosphere. I actually designed the first Department of Defense payload that went on the space shuttle. That was called STS-4. So it was the absolutely first scientific payload that was going into space. And it turned out to be a very important instrument called an interferometer, a Michelson interferometer. And I was too young to know that I should have patented that thing, and I wouldn't have to be working today. When I was asked to go to Russia, just after perestroika, and I was asked to try to find, by our government, I was asked to try to find their equivalent of our spy satellites, and also their equivalent of our geosynchronous satellites that do missile detection. And we found them, and we started a joint program. And that program is called RAMOS, Russian-American Observational Satellites. And it had a lot of experiences for 12 years. In 1988, I was inducted into the Oklahoma Hall of Fame. And one of my partners there that was also inducted, one of the others was David Boren. And so in this picture, he's on my right. And the others are all famous in their own right.
Thank you, Greg, for that kind introduction. I'd also like to thank Deborah Watson from the department, who had a lot to do with getting me here and putting this all together. I'm really honored to be here and have this opportunity, and to see so many friends and family in the audience. This is a real challenge, but 60 years of my life having fun in physics together. And then the really scary part is doing that in 45 minutes. Nevertheless, my talk has two sections, too many view graphs, of course, but they're parallel threads, and we'll walk through section 1 and then section 2. Now, as Greg has already mentioned, I grew up on a farm, a dairy farm near Canton, Oklahoma. Milked cows, bottled the milk, delivered the milk. This is a classic top of the milk bottles. By the way, you'll notice on our phone there, the 3 long rings followed by 2 short rings. was our number. Of course, everyone on the line picked up, and this was really the first beginnings of Facebook. I went through grade school and high school in Canton. I had great teachers and a great environment. In fact, I have a rumor that there's an OU freshman here from Canton in the audience. I hope to see him later. I had an early interest in science, made stink bombs, and had the unfortunate experience of having a major explosion in the chemistry lab. Well, that helped convince me when I got to OU to take math instead of chemistry. Once I got here, I was very fortunate to join a great fraternity, Delta Tau Delta, which really led to the socialization of this farm boy. I made lifelong friends, and some are here today. Learned how to ski, and my first mentor here was Joe Wolf.
Right back. And so, first physics training started there. These skis are 7 feet long, they're straight, no edges, and no release bindings. And man, you had to learn everything about angular momentum to get them to turn and stay alive on them. So that was the beginning of that. And I learned another very important thing that I've taken through my life, and that was how to play table tennis. And there are at least 2 pros in this room. One of them, I've got a picture of him here. Right in the middle is Bob Thomas, he's sitting over there. And the other one, the picture will come back in a minute, and that's Barbara Berkman, my wife, sitting right there. So just a comment, tomorrow afternoon, challenges are out for everybody. There is a ping pong table here somewhere, right? In the rec room somewhere? Anyway, that's tomorrow. Okay, the other thing I want to show you is that this group is still alive and well. We had an alumni meeting, and 4 of us are in this room right now. John Brock on the left, there in the middle, Bob Thomas you just met, and Bud Cole is here somewhere. There he is, with their wives. So that's been a great lifelong experience for me. In addition to that, from that learning to ski, while I was here learning physics, John hosts a ski trip in Aspen every year, so we call it the Stag Ski Trip. And this is the most recent picture in January of this year. John is there somewhere, and Steve Adams, who is here, is on the end in that red coat. And now the skis are 5 feet long, they're curved, and they just turn themselves. So you don't have to use physics anymore to ski. It's so easy, you know? So I encourage you there. All right. I was very lucky because I got recruited by Jensrud Nielsen. I was at the Phi Beta Kappa party, dinner or something, and this European gentleman sat down behind me and began to talk to me. And I was very flattered. I didn't have any idea who he is. But remember, I was in math and he's physics. Anyway, before it was over, he offered me a scholarship, which was wonderful, to get a PhD. So I was able to do that. Not only that, but the Air Force then delayed me. I didn't have to go to Korea because they deferred me to get my PhD. So I missed that experience. Some of whom are here didn't miss that experience.
We're sorry about that.
Right, John? All right. Professor Nielsen taught me some very important things. I learned about molecules, and I learned about infrared radiation. And I want to comment about that because the infrared radiation is very important in my career, and you're going to see a lot about what we call infrared. So for those of you who are not really familiar with it, if you look at the wavelength spectrum of light, in the visible, we see from about, ultraviolet here to about 0.4 micrometers, microns we call them, to about 0.7. And that's the visible light. Down here is ultraviolet. And all the way out here, out to say 15, 20, 100 microns, that's the infrared wavelength. That happens to be the wavelength where molecules have their signatures. It also happens to be the wavelength where a lot of the things that are important in the Department of Defense world and science occur. So infrared became something I learned enough about that when I wound up leaving here and going to Boston, I did know a little bit about it. Now, I arrived in Boston in 1956, and another new lieutenant, also a PhD from Utah State University, was there, Doran Baker, and we joined forces. And the first job I had at the Air Force Cambridge Research Labs at the time, which was the best lab in the I got to choose, so I went to Boston, assuming I'd be there and I'd come back to Oklahoma. I never made it back except on these trips. They gave me a job. They said, your job is to design instruments that have to measure a source, and they have to measure it in absolute units. We don't know how bright it is. We don't know how fast it goes off, or where it goes, or how long it lasts. We don't know its spectrum. But you got to make measurements on this that are going to be used thereafter. See, I didn't have a clearance. I wasn't cleared, so I had no idea what they were talking about. But I set out to do that. I designed some sensors that covered the visible infrared wavelength. It broke it up in chunks and measured the absolute numbers. And since we didn't know how bright or how dim it would be, I just set them up and stacked them so that I had every dynamic range you could imagine ready to go. A year later, I finally found out what it is was going to be going on. And the United States, we were in the Cold War, if you remember, back, and we were performing the first high-altitude nuclear tests, meaning they were being put on rockets and balloons and taken to high altitude. Now, not only that was happening, but I got to Boston within a year. I got to see Sputnik, just out of the blue. Looked out the window one night at 3 a.m. and there went this star across the sky, and that put a shiver down my back. Same time, we put up our first satellites that could actually measure missiles around the world. And we call that early warning. And they use infrared, because infrared is what flames emit. So you have a big signal from any kind of plume or any kind of fire. So those satellites carried sensors you could measure in the infrared. Now, I'm going to introduce you to one more science thing here. The name here I've used at the top is non-local thermodynamic equilibrium. Now, my research in the upper atmosphere was around that topic. So again, just so you know what it kind of means, here in this room, high density, high pressure air, warm bodies and everything else, you could describe almost everything going on in this room with one parameter, and that would be temperature, once you know the pressure and all that. So we would be here in local thermodynamic equilibrium. So you can describe all these molecules with that parameter. But once you got up higher in the atmosphere, and there's less atmosphere, and the collisions don't happen very fast, suddenly that doesn't work anymore. And now you've got to go into details of what's going on when molecules and atoms run into each other. So I chose at that time to call that still non-thermodynamic equilibrium, or NLTE, and it has to do with the radiation transport, very mostly in the infrared that I worked on. Any questions about that? You're not allowed either for that. All right, so what happened? I went to the field, I took these instruments. I loaded the first ones up on 2 RB-36 aircraft to take measurements of these high-altitude bursts. That aircraft, by the way, had 10 engines. You know, it had 6 props and 2 jets. I don't remember that enough. This is monster airplanes. So it's loaded with these sensors that I built. And the key players here was my friend Norton Baker and my good friend who I still work for in Boston, Jack Barber. He was a theorist. This was the engineer, and I was in the middle of it. Anyway, we measured these weapons that went off, these nuclear bursts. They weren't weapons, they were just exploratory things. Okay, this one we called Orange. It was nearly 4 megatons and it went off at 43 kilometers. And that's kind of a picture of the atmosphere, a little top with that one. Here's one about the same size. It went off at 77 kilometers. And now you notice there's quite a dramatic difference in the colors and the looks. So there's something really different going on with the atmosphere as you came on up. Then we went home, built some more instruments, went out again 4 years later in this operation, and now we put off one at 400 kilometers. It's really pretty high. It was 1.4 megaton, and there's the after effects of that. So you can see there's a lot of phenomenology going on. So we go back, I'm supposed to help figure out what this all is doing and coming from, and we couldn't understand it. None of my theorist friends, Los Alamos, were doing it. We didn't understand it. So this is when really we decided that certainly local thermodynamic equilibrium would not tell you how bright these things were. The other important thing is they totally blinded our satellites. So these terribly valuable things that we're going to watch for missile launches and watch the Russians very carefully. Any of these things go off, we're going to blind them and be out of vision for a while, which we were. Now, one quick comment here. This is really a KC-135, and it's the old 707 airplane that everyone's familiar with, lots of you, the big 4-engine jets. To do this measurements here, I put into one airplane a full 1-meter Cherney-Turner spectrometer. That means the mirror on that thing is this big. The size of that thing is there. We barely got it into the bay of the airplane. And that was going to take spectra of these bursts. Happened to be in Boston and very fortunate at a time when something called Fourier spectroscopy was just bubbling. And I helped build a little cube about this big of an interferometer, Michelson interferometer. And I hung it in another window beside this monster. Okay, that monster got nothing because the field of view was too small, it missed pointing. And that little interferometer took the first and only spectra of these high altitude tests. And it's not classified anymore, but would you believe after all those years I couldn't find one, or I would have shown it to you today. But it set me off on a path of the value of Fourier transform spectroscopy, which is part of my career. So, these were the programs that I was involved with. I'm just showing you now, we're along, 50-some years I'm talking about, 60. When you get there, try and go back that far and try to reconstruct, So here we started, and after these experiments, I began a project for the Air Force that was focused on in LTE. We had the lab, we had the field, we had theory, and early we had these airplanes taking measurements. Then the airplanes don't even get high enough. If you're looking at like the aurora, okay, and these are just pictures of the aurora seen from space. If you want to take data on those things in the infrared, you still have to get out of the atmosphere. There's too much atmosphere between an airplane even. So we put rockets, about 25 or so, 20 plus rockets over this period of time, making measurements of the upper atmosphere and the aurora. And somewhere right in here, we've been very successful, I felt. And there wasn't much more physics to be learned. And so I moved to satellites, and the first one we got on was the space shuttle, the fourth flight of it, called STS-4. One thing I didn't tell you is I helped start this lab at Utah State with Norton Baker called Space Dynamics Lab. And they became my engineering arm for a great deal of this and still are. So we got an instrument on here. NASA let the first science payload go on to that experiment. Now, I was in Florida. They had launched the space shuttle with that instrument on it, and we were all celebrating the launch. And if you ever get a chance to see a space shuttle launch, it's something you should see. I mean, there's nothing like it. It's so dramatic. So we were all kind of celebrating. I get a phone call. They were having trouble getting the door open on that sensor. This was an interferometer that was cooled with liquid nitrogen. So it had a door. The door was closed. You can't open until you get up in space. And they couldn't get the door open. So I got a phone call. Got trouble here in Houston. Get on an airplane, headed for Houston. I get on the phone. This is a long time ago. In the airplane, first phone. I call Houston, talk to them. They patched me to the astronauts that are on the shuttle. So I'm in this airplane, talking to the astronauts who are flying over the South Pole, trying to see about fixing and getting this door open. The guy sitting next to me had like pure chance. Turned out he worked for the CIA. And after that was over, he said, I don't believe this. I can't believe this, what I just sat through. Well, I was kind of stunned myself. Okay, I get to Houston, and we're trying to open that door. And there'd been a wiring mistake, and this door just pulled open from the door, and it had a little button on it. That button lit up to tell you that the door was open or closed. It had been wired wrong. Instead of wiring to tell us it was open or closed, but being in series, it was wired in parallel. So if that thing didn't close, the door wouldn't open. And during the launch, there was enough vibration, that little thing separated. So all we had to do is touch that button, and the door would open. This was the first flight the Canadians had put this huge arm on that shuttle to test it. Huge thing, that moves, the robot thing. So I was talking to the astronaut running that arm, big thing. He was trying to hit this button. So I could see X, Y, Z, where he was going with it. And we'd locate it, and he'd come up and touch and touch. This went on for maybe, I don't know, a while. Next thing I heard was, "To hell with this." And he started that arm, and he was just beating the crap out of it. I'm sure he lost his job in Canada. He was determined to get it open. He never hit that button. We never got it open. So my first cryogenic interferometer in space, we learned a lot. Didn't help it. Okay, this is just to give you a feeling now, just a visual feeling of what we're studying. We're going to study the aurora in the upper atmosphere. And you notice these colors are very interesting, and in fact they come from the same process that went on up here in this nuclear burst at high altitudes. And this is another picture of the aurora. I'll get to here later. This is actually taken from the space shuttle. It's right here, hard to see, but there's the tail of the shuttle is glowing a little bit, looking at this aurora. Okay, and here's that picture from the very high megaton burst called starfish. So we're trying to understand, think of these colors out in the infrared. Okay, that's what we're trying to measure. And by the way, the reason that you go to cryogenic sensors is that we are also warming here. At 300 degrees Kelvin, we radiate like crazy in the infrared. You'd be totally kind of blinded. So we're trying to see little tiny signals where anything warm actually dominates everything we're seeing. So the solution to that I took was to cool everything, cool the sensor completely, not just the focal plane, so that there was no warm radiation being seen. This laboratory program, it's sort of like I started a physics department, and I really did for the Air Force at my lab. We set up an electron beam of 50 kilovolts that went into air. We called it lab C. So you see this little glow? That's glowing because the electrons are being stopped in air, and they've got color, and they're putting out radiation in the infrared. And here's some of the radiation coming out in the infrared. Built a chamber that was cooled with liquid helium to about 8 degrees Kelvin, so that entire chamber had no infrared in it. And there we reacted atoms and molecules together to produce infrared radiation. And here's one of our good friends that got excited by reacting and producing nitric oxide in very highly excited states. This is the wavelength region where the radiation is coming out. The other thing that we went to was an airplane, a KC-135, Boeing 707, with a lot of instruments on it making measurements of the aurora. Rocket experiments. Some 17 carrying cryogenic sensors, all out of Poker Flat, Alaska. So every year would go up with 2 or 3 or 4 or 5 rockets we launched to make measurements of the upper atmosphere of the aurora. And a lot of these, here's the telemetry up there. Here's the entry to the Poker Flat Research Range in Alaska, just north of Fairbanks. And a lot of the players that were important in those days, very important in that program. Wait a minute, get back up now. Okay. Yeah, there you go. This is just a sample of one of the rockets. You're looking at the back end of it. Here's the motor, and here's the length of the rocket, and the instruments being worked on in that thing. This is not me. I was never that good looking. And that was in 1975. And here's a sample of the data we took with those rockets of the aurora. So we flew into aurora, and they're labeled by orders of magnitude. In IBC 1, 2 is 10 times more energy coming in the atmosphere. 3 is 10 times more. So we measured the different levels of aurora, and out of that we began to get a very interesting signal. Carbon dioxide has a very strong band at 4.3 microns. So here, as a function of altitude and as a function of aurora, is the emission of carbon dioxide in that band. This is the first data ever taken of the infrared aurora. Or look at this. And this is a spectrum of that. But you can see how that band, that 4.3 micron band, just got brighter and brighter and brighter with the input energy. Here's the spectrum of it. And over here, here's the CO2 band we talked about. And also showing up as the next important radiator up there is nitric oxide. This is the overtone, and here's the fundamental And those two molecules actually put out most of the energy coming into the atmosphere from aurora or any other excitation mechanism coming into the upper atmosphere. Now, and the resolution, by the way, the spectral resolution here is not very high. We use a circular variable filter. We didn't get into the problem. Now, this is like the opera. Am I supposed to stop there? I want to tell you theorists something, you theorists. This is one of the most challenging radiation transport problems that we ever ran into, and it's how does that radiation get out in the carbon dioxide band, nuclear or aurora. It's a very strong band. I'll give you a short message how it finally got untangled. X-rays land or high energy electrons land and bounce around. The electrons finally slow down to about 2 eV. They start at maybe 50 keV. And they finally run into an area where nitrogen has a very high cross-section with 2 eV electrons. So they suddenly excite the nitrogen. The nitrogen just happens to be in resonance with the CO2 band at 4.3. So it gives it to the CO2 band. And that's simple, it ought to come right out, right? And what happened? The CO2 band is so strong that it reabsorbs itself and it won't let the radiation out. So what finally happens is all the isotopes start to release the radiation of CO2. And so it's a long, tortuous path to get the radiation starting back here with energy out through the atmosphere and come down. It's just a fun color. Okay, we also flew a spectrometer that looked at the limb of the atmosphere. Cold spectrometer. This is the rocket getting ready to go up. And by that I mean these others were looking straight up. This one goes up and looks down at the limb. A lot of other issues involved in that. But here's the first data. We ever talked to the limb. And here's our friend carbon dioxide radiating as a function of altitude. This is nighttime. There's no sun exciting anything. And this is daytime. It's another very nice theoretical challenge. I won't go into that one. But you can see the very different views of night and day for carbon dioxide. Here's carbon dioxide at long wavelengths, 15 microns. And here it is falling off, and suddenly we get up here around 100 kilometers, and it increases. Another mystery. Turns out that this is the beginning of where atomic oxygen is in the atmosphere, starting to be a big component of the atmosphere, until just N2 and O2. Suddenly there's a resonance with O, and that drives in its function, which became very important in understanding a lot of planetary data that was being measured. Why carbon dioxide is radiating away at us. And this is where it's coming from. So finally, all of the infrared molecules that we can measure, water, CO2, carbon dioxide, ozone, are all as a function of altitude from this one rocket flight. And that's one of my more important papers. It wound up as a very important part of the Handbook of Geophysics, which I just happened to be editor of at the time. Okay, now, all that activity with Fourier spectroscopy, and particularly in the laboratory, out of the blue, I show up in a collage of pioneers of Fourier transport spectroscopy, and this is an American Institute of Physics in the Archive of Applied Optics here, 1972. Here I am in the corner. I know you never recognize the hair. But the other thing I'm proud about this also is that I've got pretty good company. This is Fourier. Okay. This is Michelson. This is Lord Rayleigh. And there's some good friends in here that you wouldn't know the names of necessarily. I'm convinced the only way I got in here is that I actually was the inventor of when you do a microfilm interferometer, to take spectra, you have to take a mirror. You have to scan it to get it to take spectra. And that mirror, if it doesn't move really smoothly, you have a kind of a mess on your hands. So I'm the first one who put lasers in here to measure exactly how to sample. So the mirror could slow down or speed up. We still sampled it exactly correctly with the optical path. Well, I wasn't smart enough to patent it. But what I did is I sent my team over to France. We had two very famous astronomers, Janine Kahn and Pierre Kahn. We showed them how to use it. We also took over the Fast Fourier Transform software program that I brought into there. And it just changed the world. Now, these instruments, in case you don't know, these interferometers and Fourier transform things, are in every chemistry laboratory, every industrial laboratory, almost every physics laboratory in the world. And they all use that laser. Just found out I wouldn't have to be working today. But anyway, that was a very exciting thing I learned. First microsynth interferometer, cooled, put on a rocket looking vertical, before we went to the satellite, was called Hyris. And the people building it for me were at Honeywell and another small company, a great friend, Adila. This thing went up. This is also a big lesson. We got the door open this time. I get the data. I'm supposed to give a talk on the data. I'm looking at the data, and it just purely black body. And there's no atmospheric species. There's no CO2 or anything else in there. Okay, we learned something. The engineer didn't pull this door back far enough. This door is warm. And this door scattered and hit these baffles and completely overwhelmed the signal. Okay? So I gave up on Honeywell and went back to the Space Dynamics Lab at Utah State University. One other quick science experiment. We made our own aurora. You know, we're also trying to simulate the amount of energy coming from a nuclear detonation, which is pretty intense. And aurora is kind of out here on the small scale amount of energy hitting the atmosphere. So I collected every smart person I could in Boston, which was a bunch of them, and came up with what we should do. So we put an electron generator into a rocket, and we fired 3 kilovolt electrons into the atmosphere, and we made our own aurora. Now I had at least 10 to 100 times more energy going in the atmosphere than from the aurora itself, and I could control it. Okay? The final of 5 of these experiments we flew during this program, we flew kind of the ultimate experiment. We flew what we called the mother daughter. We put the electron beam and fired, made the aurora. We dropped off the sensor payload flying along with the mother and the daughter, and then we looked at the measurements of this aurora, just really up close, but off of the payload itself. And this worked beautifully. Here's the rocket, the White Sands. This is my team of the whole team there. This is 1990. And lo and behold, if you look at the spectrum, I know you can't see back there, but here are 2 of our wonderful friends. This is CO2 at 4.3, and here's nitric oxide out in the 5-6 micron region. What that really found and what we wound up with is that the largest percentage of energy that radiates out from aurora is actually in those 2 molecules in those bands right there. And I put a number on it once. I forgot what it was. It's the percentage of energy that came out of the atmosphere. I can't remember. But it wasn't huge, but it was, it was where all the energy comes out, where it radiates. All right. This is a picture of the cryogenic interferometer that can look at the limb. This was done by Space Dynamics Lab at Utah State. This is still up there on display. It went up on in 1991, and it was on this payload right here, looking at this aurora and the upper atmosphere. And this had come after the Strategic Defense Initiative was started, and my good friend Barry Katz helped sponsor this, and it was a great success. In fact, it was so successful that I quit doing this after that. We had everything I knew how to do, all the instruments. I think we had most of them. Not all, but most of them. So, at the end of this program, so to speak, it started here. All of the fundamental science of these projects went into codes, computer codes. Most of it's in the unclassified literature. A little is not. But living today is the code for the nuclear optical and radar systems effects called NORS. And my company is a curator of that. And we've also shared it with the UK. So all of that information about predicting and knowing now what goes on in the atmosphere is still alive. And if you hurry, we can still help you get it. Be glad to get it out. So that kind of came to the point of the first part of my talk. My talk really has 2 threads. That was the first part, and that whole theme. The second thing I wanted to show you is what all was going on in the world that really affected my career. I've already told you about bees and this satellite early warning system. and the Nuclear Test Ban Treaty started. And that made money available to study this stuff. I could never have had the funding for that without this having happened. And that's what fed us to do this work. And then we signed the Anti-Ballistic Missile Treaty. I was very involved in the things I was going to do. We started Star Wars here, and I was very involved with that. And something interesting, very important happened out here. You may or may not know about this, but we nearly had nuclear war. The Russians were on alert. They're still on alert. Everyone's set to launch these missiles. 1,000 missiles. I don't want to go there. But at one time, the Russians' early warning system picked up, they thought, an American set of launches, like they thought 3 of them would come. And this colonel, Stanislav Petrov, had the job to push the button to start launching in retaliation from the Russian missile silos. He didn't do it because he thought, it doesn't make sense. I see 3 what appear to be, but he's supposed to, he sees 3 incomings. He didn't do it. And I guarantee you, it'd be a different world had he moved. Now he got reprimanded for not following his protocol and his orders, and he retired as a lieutenant colonel. And it's well-known history if you want to look it up. But it really made a difference to the kind of study and research that we were doing related to missiles. Okay, about 1990, perestroika came in Russia. And you'll see, I started programming here related to that. That's the second part of my talk, really. And the other thing that happened here, out in here, is that President Bush, we withdrew from the ABM treaty, and that made a big difference also in the work of it. So, things that happened to me along the way, some of which I've mentioned. Right here, started this laboratory, which is really well known now. It has 300 people. It's put 1,500 students through the lab at Utah State University over this period of time, and I'm still very closely tied into them. Right here, I sponsored the Fourier conference on Fourier transform spectroscopy. That red book, you still have it. I meant to bring it down. But I'm proud of that because out of that conference, I think is the Bible still for Fourier transform spectroscopy. And that happened in 1970, and it happened in Aspen, Colorado. I can't imagine how far out there. But that's really good. We had a great snowstorm that year. Okay. Along my career, at the end of my career as a civilian scientist, I got out of the military right here and signed up as a civilian scientist. I became the chief scientist of the Air Force Geophysics Lab. It changed names at that time. And then I retired, and I've been on my own, so to speak, since. I joined Visinine, a small R&D company. And right here, out of the blue, I got elected into the Oklahoma Hall of Fame. I'm very proud of that. And also right in here is when SDIO began, and I helped form and help move that program. Vice President, I won't say much more about that, except what we did in here with about 40 of us, 40 scientists got pulled out of academia, out of wherever, and we reviewed everything going on in the classified world. And there was a decision made by Clinton right here, and we declassified 800,000 images worldwide from our satellites and our rocket and everything. And we got the Russians to also agree to declassify a lot of stuff. So we had an impact there. Now, this is where I started the Russian program, and I'll talk some more about that in a minute. And then I had one more satellite in my pocket. So just comment here, right in here. I'm very honored I got selected as one of the top, most influential Delts, top Delta in the 20th century. And those guys, some of them are out here. I'll make them fess up in a minute. I can't quit. I'm still happy. My latest, what I consider major paper, was just published last week in the Journal of Geophysics Research. Okay, Hall of Fame, 1988. You may or may not recognize the players. This is me, because in case you don't know. This is K-Star, a wonderful country singer from Oklahoma. And this guy in the back on my right, you recognize him? Okay, that's David Boren. So we do have one thing in common. This is the satellite. I only have one view graph. Now, I haven't described this to you, but I helped bring this satellite to fruition, designed what it should do. It was a cryogenic system. In this case, its job was to track ballistic missiles after the plumes are down, decoy the real thing away from to discriminate the real thing away from decoys, and prove that if you used infrared and you did it right, you could really make this stuff work. You really could track and locate and shoot down ballistic missiles. So it's part of the SDI overall time. And there's some very important players. First of all, this sensor was built, again, by Space Dynamics Lab. It was an 8.5 degrees Kelvin. It had an interferometer and a radiometer, and it had a big mirror. So liquid helium for a year in space, cooling a mirror like that and making it work well is no trivial exercise. Program managers over the years, Bruce Gilmain is still active. I talk with him regularly. He is at Utah State today. All right. Another thing that was fun. Remember I told you we had the environmental task force to examine our classified assets to see how much of it could be used for environmental purposes. And so we had to also convince the Russians that we were serious and we wanted to do this. So we made a number of trips to Russia. This happened to be, don't get carried away, this is a balloon. This is my friend who's a KGB kid. Barbara knows him well. It's Boris Danilov. And back here is this lady, Linda, that ran it. This is a group of professors and scientists in Russia, a normal, nothing Russian meal, working there on this issue. Oops. So, started a program called Rainbows, Russian-American Observational Satellites. So it started here, this happened. I was asked by our government at various levels to go to Russia, get a team, find the Russian space scientists and organizations, the best ones we could find, and see if we could enjoy work together. And of course, they had just come apart in Russia. I mean, it was really a disassembled state at the time. It was now the Russian Federation. And so we started this initiative right here. You're going to see a few samples where we had the two satellites work together. We used our airplane, and we did a set of airplane experiments. And then we started the two satellite dual-use experiment, which really the Rainbow satellites really began seriously in here, and ran 12 years of my life. And it ended rather dramatically. It had a lot of reasons, but fundamentally, when we withdrew from the ABM treaty, there was a lot of political decisions that we didn't need to have this joint effort anymore with the Russians. It was a tremendous loss of opportunity for the United States and for the Russians. But we've continued with the science from that, and I can tell you a little bit more about it. We did some experiments that started in that program here. We're still working on it. And we have a measurement program even here in Oklahoma that is a spin-out from some of the technology from that program. Now, to help that program happen, I want to show you a few people that are important. We formed an advisory group at the Space Dynamics Laboratory at Utah State. And in here, I'm in the middle. Peter Banks, who's written books on the upper atmosphere, along with Professor Stanford at the time. Senator Jake Garn at the time. And this man in particular is Benny Schriever, retired general, who actually created our ICBMs. So he was the guy that Eisenhower gave the job of beating the Russians to ICBMs. He was retired fully. He was a little older than I am at the time, but he was still active and he was very helpful. You walk with him into the Pentagon or anywhere else, I don't care. The door opened, he came in, you sat down and you had a discussion. It didn't matter who you was with. So he was very helpful to us. And then finally, this is General Schriever that I'm still working with today. Very helpful in that Russian program. And finally, we got it to happen. The Russians didn't trust us at all. So we had a lot of very tense moments. I did the dumb thing of, I said, let's do this the American way. Let's go over, find 2 or 3 organizations, get them working, and we'll compete. And then we'll select the one we want to work with, right? Dumbest thing I ever did. We actually got the top group, who is really the same as our NRO. That's the National Reconnaissance. That's our spy satellite organization. At the time, even the words were classified. They're not anymore. But we got that group in Russia to work with us. Those are low altitude satellites, so you can make imagery. And then we got the group who looked for missiles, very high altitude satellites, like I was doing, geosynchronous. Okay. And the guy who is head of the Russian geosynchronous satellites is this active division 7. Now both of these guys that headed these groups, Guskov and the other one, were giants in Russia. They were competitors. They had never sat in a room together, the two of them. When we went through our mini trips, and we suddenly got both of them in one room one day to talk about what we were doing. And those two guys, man, was it tense. Not only that, but Russia had decided we had stepped over the bounds. So I spent the most nervous 10 hours of my life in that room with the newly returned KGB and all the reasons we had broken Russian laws, of which there weren't any when we started this. But those two guys actually stepped in and kept us, I think, from putting me in jail and still being there, out of that room. So it was a very tense meeting. We got out of there all right, but if these two guys hadn't been in there, I'd still be there, I'm sure. And Savin is a very interesting guy. When he was a junior in college during the war, they pulled him out. He designed the artillery and then oversaw the building of thousands of them that defeated the Germans and saved St. Petersburg. So that's the way he started from his college days to go on to where he became. And he has 2 medals of Lenin. He's just a genius of a guy. And he's the one who, for this program, one day said, everyone was saying, get out of here. And he's a guy who tapped down the Russian generals and said, let's play this out. Let's see where it goes. And we were on our way to a very, very good technical scientific program. First part of it, we did a little science with. I was chief scientist of an MSX satellite, and we combined so that we saw the South Pole region from their satellite. And so we took over 1,200 measurements together of the same scene, and we reconstructed in 3 dimensions Mount Erebus, McMurdo Station. You can see those from different views. And the reason we did this is that Ramos itself, as you'll see in a minute, was designed to have 2 sensors, passive sensors, so you could form a track, so you had stereo. So this was the beginning of our demonstrating how to do that. It worked very well. We also had a program with the airplane that I told you about, where the Russians brought over the radiometer in the infrared to measure water vapor. The Space Dynamics Lab put an infrared polarimeter on board the airplane, and Vince and I put on, now I wasn't with any of these at the time, I was just the chief scientist. We put on the LiDAR to measure the range and altitude of the clouds that we were measuring. And so you can see the team, almost half Russian and half otherwise. And this airplane has all these infrared windows, it has periscopes, etc. This is called Vista. It's a very dedicated airplane for doing these kind of measurements. We ran those from 97 to 99. And here's part of the science team. You probably don't recognize me, but I'm there. And this is Dmitry Zhvanov, who still we work with, and these are the Russian scientists and engineers, 2 of them at least, who were on the airplane with us. Oh, by the way, just for fun, well, I don't see it up here. This is our logo. So here's the Russian satellite, here's the American satellite, and this is the logo we used for the Ramos program. The airplane that I just told you about and flying, we did some things like we'd circle around a cloud formation, and we measured the angles of the solar scattered light and measured the angle of polarization in the infrared of the polarization of light being scattered by the clouds. We also measured the water vapor in the atmosphere, the clouds themselves, and the altitude of those. And we did the stereo reconstruction from a lot of our data for the same purposes that I mentioned before, because we were headed here. We were headed to these 2 satellites, a Russian satellite, an American satellite. They were going to be able to track any kind of missile or any kind of target. In this case, a cyclone. These would actually measure the intensity of cyclones and predict their intensity. And you can only do that if you knew the altitude and the temperature of the eye wall. So there were a number of things like that that we set out to do. The players in Russia were Rockwood Kometas, which is where Savin is the director, Astrophysica, another one. And then on our side is primarily Space and Networks Lab, there's the Prime, Visidyne, was the Science, and Aerospace Corporation. These were the principal players. We had a lot of interaction with a lot of important people on both sides. This is technically the last thing that wound up. We did build a satellite. This is the Russian Ramos satellite. It's the engineering model. They're in the clean room. This is Dr. Shnelsikov, Dr. Matrushka, and Dr. Glinov, all principal engineers and players of that program. And that went on display at various shows, internationally. They were in Paris at the air show and something like that. So that was the last, though, before we shut down. And then here was a celebration, typical classical celebration in Moscow. And I don't know whether she recognizes herself, but this is Barbara. And that's not a martini, very rare. Anyway, she made a few trips, a lot of us made a few trips, and we had some great fun during that time. And finally, 6 years after Ramos ended, last year, I got a poster from them, from the Russians. And it's right here. And except for being a little bit too me-ish, I urge you to read it because it brought tears to my eyes. It was my 80th birthday. This came to me in Russian, by the way. Like they think I can still read Russian or something. It got translated, so it's readable. But here's the Russian team, part of the Russian team of engineers. Sent that to me in pictures here about what we did together. And I just pulled a quote out of one of them that's here. You can read that about our cooperation. And I think what we did is we really did reduce the Cold War tension. Unfortunately, it's not maintained itself and not there, but that team is still working. Now to end the talk, I just want to end up, from that work, we knew we had to measure things like clouds, what was going on with clouds. We built a sensor just to do that. It's called SAM. It measures the sun and the aureole from the sun. That's a measure of particle size distributions in the cloud between you and the sun, like cirrus clouds, for example. We've had one for 2 years up in Oklahoma at Vermont at the ARM facility. We have one in Spain, which is not in a dome, but this is it right here, tracking the sun. And the reason they're using it is in solar research, they're very concerned if you want to heat this stuff up with imaging the solar disk, the slightest bit of cirrus or something scatters that light and reduces the signal that you have to use for heating up the thermal. And so it's some study there. We've had one at Goddard, NASA Goddard. In fact, the work coming from here with the MODIS instruments on the Aqua Terra NASA satellites are the results that went into this article that just got published in Journal of Physics Research. And the thing I'm proud about that is that we were ground truth. For 12 years, the data from MODIS has been the main thing used for radiation transport from cirrus clouds, how much radiation balance they cause and what cause. And I think we have convincing evidence that their retrieval algorithms are off by a factor of 4 to 8 in the optimal depth of the clouds, particularly cirrus. So it may or may not help improve the stuff that goes into the climate models that we use. And we know that's a good question. So the last thing I want to say is that just November, December, Visidyne joint venture, this New World, a joint company with a company in Canada. And my friend Eva Bleek is shown here. We just started this to use for remote sensing and safety of aircraft in the aircraft industry, the aeronautical industry. And this is in Visidyne. This is my office. And the mayor of his town, Saguenay, had to fly down for the actual start of this. And I hope that was all worth it. Now, in the talk, I ran over that. The real hard questions that you're going to ask me, I know, about what went on area of Nevada, you know, are the aliens real? Those who really want to know about the truth on global warming and climate, I'm supposed to have brought a professional. Dave Turner in this audience? Right over here. So we really want to ask that question. There he is. Okay. And if you really want to know what the Higgs boson is and have we found it or not, I met him at lunch today. Where is he, Pat? He's right over there. So I really brought in some ringers for the tough questions. They're here. So thank you very much.
It's great to have A.T. Stair here and give such a marvelous colloquium. I very much enjoyed it. I'll leave it open for questions. I will start. One of the questions you were asked this morning was what advice you would give to graduate students. Us as faculty can give advice to students as they're getting employed if they're going into academic industries. But you didn't do that, and so what advice would you give some of our students?
Are there any students in here? Ah, there are some. I guess from my career, which is pretty long now, what I would say to you is when you leave here and get out into whatever position you take and wherever you might move to, the most important thing you can do is look at what job you've got. I wound up in Boston, I looked around and, you know, and whatever the opportunities in there, make them happen, make them happen. Get in the mix, be out in the action, because opportunity actually only comes when you're out there, when you're really doing it and you're traveling, you're meeting people, and you're in your field. My wife calls that karma. If you're out there, things happen, be active and proactive, and those pieces will come together that you really enjoy. And then you make those happen. That's where you go. But you have to really push it and take advantage of that opportunity where you are, and push, and karma will come.
A.T. over here.
Oh, hi, John. Yeah.
A lot of your research had to do with CO2. Does any of that research have any relationship to the greenhouse effect that you keep bringing up?
I don't think so. No. The CO2 I mentioned here, and all of those things that happen, really have to do with how the atmosphere radiates its energy away. And down here where we are, which is really still where the CO2 and global warming and climate change will happen, are still basically a temperature-controlled local thermodynamic equilibrium. So those things were all happening outside of that realm, and I don't think it applies. I don't know how it works. So, yeah.
I will let you ask a few more questions after I present A.T. Stair with a gift from the Department of Physics and Astronomy. This is a picture of the current Nielsen Hall after it's had 2 additions on there, which is Ryan Duzma's here. He's was the one who got those 2 additions put on the building. We would like to present this to you. We will also send you a photograph of the picture that we just took at 3 p.m. today. We thank you for joining us for that part of it. I'd also like to make another announcement. And Barbara, could you come up?
I'm not great.
Okay, you're not going to come up? Okay. So Barbara is very successful in her career in geriatrics, has also received numerous awards for her research and efforts. But she is also giving a generous gift to the Department of Physics and Astronomy and for graduate scholarships. And we appreciate her for this marvelous donation.
Thank you very, very much. I'll treasure this. very much, as you can tell. I'm very connected with all of you all. And let me comment on the second one. And when Barbara and I talked about what was really important here that we might have some effect on, and that is that we didn't see enough graduate students. And so we decided if we could, what we should do is really just set up a scholarship fund that would help scholarships for more graduate students. So we're going to start that, and you'll be hearing from us. So we hope that will come together and bring more money to the fund to help. And at the table even today, as I talked with you professors and the young ones, is the main thing Barbara said to me, she says, there's not enough graduate students. And that's really the case. And we need to really make that change. And so that's one of the thrusts that we really are trying to make happen.
And it's going to be in AT's name, so his legacy will live on.
It definitely will. Thank you. Additional questions?
You say the future of the Russian space program is fighting or exploding.
Speak a little louder, Jim.
I guess I was just asking if you have any insight into what the future of the Russian space program, satellite program is, since fighting or exploding.
You know, I really don't know currently. I can tell you when we were there, and we were there 3 or 4 times a year for 12 years almost, it was in shambles. You know, that they had just imploded. And that whole country was controlled from the top, and they never had to worry about raising money or anything. It was, if someone decided to go do something, it got funded, and you went off and did it once you convinced the powers that be. We were trying very hard to help them, actually. No one would believe this, but it's in our interest that the Russians have good early warning satellite capability. That mistake that the colonel did not make, the smartest thing we could do is to have good information about those problems, missile launches worldwide, so that no one makes a mistake. You know, you need to know what is it, where is it coming from, where is it headed. And so part of this program that I really was set out on to do was to do what we could jointly to improve that information availability to the Russians, to us, and to other countries. That was really part of the underlying theme. Today, I don't know. I really don't know anything much more than what you would read in the paper or go and Google. I don't see very much improvement. I don't see much commitment yet that I know of. They're very competent scientists. Trust me, very competent scientists. But I just don't know how much commitment the country has made to this problem. What I'm sad to see is that just last July, I did get to participate for a week at Stanford in one of the think tanks with about 10 Russians, high-level Russians, and 10 of us trying to restart a joint activity. This was actually run by George Shultz, remember our Secretary of Defense, I guess he was, and other high-level people. I don't know how I lined up at these meetings, but I was there. And we came out of there with a very strong thing to let's get re-engaged. And the Russian administration, I'll put this on Putin, turned it down. They turned it down. They said, well, because this is tied to missile defense, and we don't like what you're doing, even though it has no threat. I mean, I know a lot about what we're doing over there. We're putting up some defense for Europe. But he turned it down. So I don't know whether it can change or not, but it has to change at the very high levels for this to come back together. And whether it will or not, I don't know.
We have time for 1 or 2 more questions. Okay. Let's thank AT students.